So it turns out once again that somebody might have said something on the internet that is maybe not quite entirely true. And it was about quantum mechanics, which is fairly common. I got this from reading Stephen Novella's blog on thenest.com. It was about exorcisms, so nothing to do with quantum mechanics until we get to the comments section. So I don't really want to pick on what he was saying or really argue metaphysics about demons or angels or other supernatural things. It's just that he happened to give the most perfect quote about quantum mechanics that really sums up one of the biggest misconceptions about quantum mechanics out there. So what he says is that it's remarkable that someone who believes in multiverses and quantum entanglement and simultaneously dead and alive cats would criticize someone else for belief in magic, therefore effectively equating quantum mechanics with magic. So let's look at exactly what is magic, besides being the popular card game. Let's go to Merriam-Webster's definition. From there, we see that magic depends on something having influence or power from a supernatural source, or use of means to have supernatural power. At any rate, magic relies on supernatural. And supernatural, by literal definition, means something that is above natural. Something that is supernatural cannot be natural. The problem with relating quantum mechanics to the supernatural is that quantum mechanics is a physical theory. Quantum mechanics was made to describe physics, which is natural. So since quantum mechanics describes what actually physically happens in the world, that means it is by definition not supernatural. And it absolutely cannot be used to support anything that is supernatural, that is not within the realms of quantum mechanics. Let's look at what quantum mechanics is. Quantum mechanics is, instead of looking at a particle in terms of, say, a packet or just a hard ball of something, we're considering it to be a wave. It's not special things that are quantum mechanical. Everything is quantum mechanical. It just depends on whether you're on a scale that your wave function is meaningful or not. So a wave function can be any sort of arbitrary shape in space. The only limitation on it is that it satisfies the Schrodinger equation. The issue here with a wave is that positions are not typically well defined in a wave. So say we have some arbitrary wave and it's existing in space, and I make a measurement and I measure my particle to be at point x equals c. Well, there are three different approaches to this idea. One is the realist approach. This is the approach that Einstein took up, and that is that the particle was always at point C. We just didn't know it was at point C. So basically what he's saying is that the indeterminacy of the position of the particle has more to do with us being ignorant than it has to do with nature. This would mean that quantum mechanics is an incomplete theory. This would mean that the wave function is not telling us everything there is to know about the particle. This would mean that we would need to complete the theory of quantum mechanics, or another way to put that would be, it would mean that quantum mechanics could not be wholly predictive. Another position is the agnostic position. This is, I don't want to answer that position, which sounds very silly, but it's not that silly. The way that Griffiths puts it is, quote, "It is metaphysics, in the pejorative sense of the word, to worry about something that cannot, by its nature, be tested," unquote. So, first off, I would not use quantum mechanics to support metaphysics, given how people who have developed quantum mechanical theory viewed metaphysics. They weren't really on your side, just as an aside. But what this basically means is that since there's no way to know where the particle was before you made the measurement, then it's a silly question to even ask it. Or in other words, if there's no natural way to know where the particle was before you made the measurement, then it is outside the realm of physics to even ask the question. The last position that was a viable option until, say, the 60s was the orthodox position. That's the particle wasn't really anywhere, so as you can see, this wacky wave function in space doesn't really define a particular location until you made the measurement, and then you collapse the wave function at that point. This would be the Copenhagen interpretation. So it's not only the fact that the observation disturbed what's to be measured, it's that the observation made it at that point. It produced the position. So until like the 60s, these were all three viable options. However, the work of Bell really narrowed this down. So in 1964, John Bell, and I'm sure plenty of other people, a bunch of grad students who never got credit, made an observation. So this is not a theory. They put this out of the realm of hypotheses and into the realm of experimentation. So they showed that there is an observable difference if the particle had a precise position before the measurement. Even if you don't know what that position is, the fact that the particle has a position before you make the measurement affects the measurement. So that completely takes out the agnostic position. And this is just, by the way, a mathematical thing that Bell showed. He showed that there is a mathematical difference if the particle has a position, even if it's not known to the experimenter, before you make your measurement. So he took it out of the realm of hypotheses, put it into the realm of experiments. This is something you could test. He made a way that you could actually test this. So it became experimental result whether or not realist approach or orthodox approach is correct. And the experiments that we have support the orthodox position. Now, this is really not such a strange idea. This idea is not unique to the quantum world. Like, let's look at just what a wave is. Here's two examples of a wave. You could have a pulse, where we could say measure the position of the pulse, its time. We could get its velocity or its momentum. It's very well defined. But what's its wavelength? That's not so well defined. Or you could have like a standing wave. Here you can measure the wavelength very easily, but what's its position? Like, think about if you have waves in the ocean. You don't say the wave was at, x equals 3 meters, y equals 4 meters away from you. It's a little bit nonsensical to say, where are the ocean's waves? Well, they exist in all the ocean. That's all you're doing with quantum mechanics. You're just saying that the particle is a wave, and until we measure it, it isn't really well defined where it is in space due to the fact that it's a wave. So it's just not the case that quantum mechanics is inherently mystical. It's not mystical at all. It is a physical theory. All it does is describe the world in view of waves. Instead of viewing things as just packets like you do in classical mechanics, when we're on a scale that's appropriate, we view them as a wave. And all these things that are weird and strange about quantum mechanics are coming from the fact that it's a wave, not a packet.